In this video, we'll look at the terminology that's used when discussing probability and how to calculate the chance of something happening. We'll look at constructing sample space diagrams and probability tables, and then use relative frequency to state the probability of future events. Here we have a probability scale, which always starts with 0 and ends with 1. These represent the two ends of probability, with 0 being an event that's impossible and can never happen, and 1 being an event that's certain to happen. These can also be represented as percentages, as well as decimals, but in most instances we'll be using fractions to represent probability, more of which in just a moment. If 0 is an impossibility and 1 is a certainty, then in the middle between them is the point at which we can say something has as much chance of happening as not happening, and this is called evens, and it's calculated as a half or 0.5. In real life, there are very few, if any, events that can be described as impossible or certain. So the chance of most events usually occupies above the evens mark, which we'd call likely, or below the evens mark, which we'd call unlikely. We'll look at defining these further, but they may ask you to use words to describe the chance of something happening, in which case these are the words to use and the ways to use them. Exam questions are one of the only places that it's okay to talk in such definitive terms as impossible or certain. For example, they may say, what's the chance of the sun setting at midday, which would be categorised as impossible, or the chance of Christmas being in December, which would be an example of a certain event. Throughout this video, the simple fact that a probability of an event cannot be greater than 1 or 100% or less than 0 or 0% is crucial. In order to calculate the likelihood of something happening, the simplest way to display it is as a fraction. The way of getting what you want, or the success criteria, over the total possible outcomes. Sometimes this is written as P, meaning probability, and then success criteria, which will be in brackets. If we put this as a fraction first, we can always calculate the decimal or the percentage from that. But it always starts off as a fraction, so it's easiest to think in these terms. In probability, there are some cases that you cannot simplify the fractions, so very often you're not asked to. And I'd suggest not doing so with a probability, unless they ask you to as part of the question. Let's think of a few examples of probability. So the chance of tossing a coin and getting heads, or the P of heads, would be 1 head on a coin out of 2 possible outcomes, so 1 over 2. How would we write the possibility of getting a 6 on a fair dice, or the probability of 6? Well, that would be 1 chance out of 6, so 1 over 6. We'll look at the distinction between fair and biased in a few minutes. The probability of choosing a picture card from a deck of cards, or the probability of picture card, would be 12 picture cards out of 52 cards in a deck, without the jokers, so 12 over 52. These were some simple examples of calculating probability. Now we're going to look at using tables to write out all the possible outcomes in order to calculate the chance of something happening. And we'll start with sample space diagrams. In this question, we have 2 bags with counters in them, which all have numbers on them, bag A and bag B. A number will be picked at random from each bag and then added to get a score. We're asked to calculate the probability of a score of 10 or more. In order to see what the total possible outcomes could consist of, we can draw out a sample space diagram with all the counters from bag A and all the counters from bag B on the axes, and then fill in for all the possible outcomes. For the top row, we do 1 plus 2 equals 3, 2 plus 2 equals 4, 3 plus 2 equals 5, 4 plus 2 equals 6. And we could do this for all the rows until we've completed the grid. Once we've done that, we can see the numbers that are 10 or greater and that there are 4 of them. We can also see the total possible outcomes, as there are 16 of those, so we can give the chance of getting a number 10 or greater as 4 over 16. Sample space diagrams are a great way of showing the total possible outcomes, and very often we're asked to do something similar with menu choices or the outcomes of a race. The sample space diagram forces you to consider all of the options rather than just the first ones that come to mind. Another way of displaying probabilities is via a table which uses decimals to display the probabilities instead of fractions. Let's have a look at one of those now. Here we have a bag of marbles, and the probability of choosing from these 5 colours is shown for 4 of them in this table. It's important to know that these are the only 5 colours that are in this bag. We must remember that all probabilities will add up to 1, and the chances of picking these colours is seen here. We're asked to calculate the chance of picking an orange marble, and then, given that 35 of the marbles are blue, to calculate the total number of marbles in the bag. As we know all the probabilities must add up to 1, we can add the other 4 probabilities to get 0.88 and subtract it from 1 to get 0.12. So this must be the probability of choosing an orange marble. Now we need to calculate the total amount of marbles in the bag, given the fact there are 35 blue marbles. Well, if the chance of choosing a blue marble is 0.14, that would be the same as saying that 14% of the marbles are blue. So we can find 1% by dividing 35 by 14 and then multiplying it by 100 to get 100%. So 35 divided by 14 times by 100 will give us 250. So we can state there's 250 marbles in this bag. Now we can look at relative frequency, where we take an experience or an experiment that's taken place and use the results as the probability to predict future outcomes. In this question, we're told that a dice has been rolled 60 times with the following outcomes. It's come up with a 1 twice, a 2 9 times, a 3 11 times, a 4 8 times, a 5 12 times, and a 6 18 times. Given these results, we're asked if A, do we think the dice is biased and what our reasons are, and B, if the dice was rolled another 240 times, what would we estimate the number of times 6 would come up? So firstly, do we believe that the dice to be biased? The concept of fair or biased is a common one in probabilities, and bias is defined as a disproportionate weight in favour or against something. We're asked to make a judgment based on the evidence from this table, so let's consider the probability of this outcome. Theoretical probability is that the number on a fair dice should come up equal as much as any other. So we should therefore have 60 divided by 6 numbers on a dice would give us 10. And so we should have 10 of each number. However, we know that real life rarely runs according to theoretical probability. So we're being asked how far we get from these figures and still be believable that the dice was fair. Would you believe that we could get 11 of a number and 9 of another? Yes, probably. What about 12 of one number and 8 of another? Well, yes, that could also happen. Let's look at the extremes of this example. Do we believe that we could get 18 of one number and only 2 of the other, which happens to be on the opposite side of the dice? That is still possible, but it seems very unlikely. So I would state that yes, I believe this dice is biased, as I don't feel it's likely to get almost a third of the outcomes as 6s. We could always state that we need further experiments to be more certain, but on this evidence it suggests that it's biased. There could also be an argument for this being unlikely but still possible, but if we look at this in the context of a GCSE exam question, we understand what it is they're looking for. Darren Brown, the TV illusionist, once showed that he could toss a coin and get 10 heads in a row, and did so on recorded TV without any cuts or edits. However, he then went on to explain that he spent over 12 hours filming the tossing of that coin in batches of 10, and the batch shown was one of thousands of attempts he made. The fascination of probability is that something can be very unlikely to happen to you, but very likely to happen to someone if lots of people are doing it. We're then asked to consider if the dice was rolled another 240 times, what would be our estimate of the number of 6s to come up? As we got 18 6s out of 60, we can take that as the probability fraction and use it to calculate what that would be out of 240. 240 times 18 over 60 will give us 72. So we'd estimate that 6 would come up 72 times over the next 240 rolls. So in this video, we looked at the terminology of probability and the words we would use to describe different probabilities. We looked at how to calculate the probability of something occurring, using the success criteria over the total possible outcomes as a fraction. We used sample space diagrams and probability tables to represent the possible outcomes, and then used relative frequency, which we defined as a previous experience to calculate the probability of future events. In the next video, we'll be looking at probability and frequency trees. I'll see you then.